Welcome to qnawire.
We know that this system has translational equilibrium, the x and y directions, static equilibrium. So we can apply Newton's second law in the y direction. This would be equal to the force normal minus the weight mg. This is equaling 0, and so the force normal is equaling mg. We can apply the sum of forces in the x direction. This is giving us the force of friction equaling mass times the acceleration. And so we can say that the acceleration, the linear acceleration, is going to be equal to the force of friction divided by the mass m. The sum of torques about the center of mass would be equaling force normal times x minus the force of friction times y. This is equaling 0 because, again, the system is in static equilibrium. We're going to combine these equations to solve for the acceleration. So we can say that, excuse me, force normal times x minus the force of friction times y. This will equal 0. And so we can say mg times x equals ma times y. And so mass cancels out, and the acceleration is equaling the acceleration due to gravity times x divided by y. This would be our answer for part A. For part B, based on the form of the solution for the acceleration, a equals, again, x over y times g, we can say that in order to minimize the acceleration, a min, we would have to x should be as small as possible. And then y should be as large as possible. We then know that the rider should move upwards and towards the rear of the bicycle. This would be for part B. And then for part C, they simply want us to solve. So the acceleration is equaling x over y times g. This would be equal to 0.35 meters divided by 0.95 meters multiplied by 9.8 meters per second squared. And the acceleration is found to be approximately 3.6 meters per second squared. This would be our answer for part C. That is the end of the solution. Thank you for watching.